welcome everybody to this final session of our conference. Sorry, for the late. We have some small issue, technical issue that we hope we have solved now. So sorry again for this late. And
okay, yes. So we are at the last session. So I remind you, we are going to have 3 talks and then the awards for the flash talks and some brief, short concluding remarks. So we start with Anna NELLES, who is going to tell us about the future facilities for high energy neutrinos. Please, Anna.
Okay, thank you. I could turn on my video, but it says that the host has not stopped it. So as long as you see my slides, I guess we're fine.
Yes, we can see your slides.
And now you should also be able to switch on your video.
Yes. Okay, excellent. So even though we're all remote, at least
yes,
it feels a little
now
bit.
we can see you.
Now it feels a little bit like you can see me. Okay, thank you very much to the organizers for giving me the opportunity to talk about future facilities for high energy neutrinos. And well, I gave this a subtitle that says, of course, a personal selection, because I'm sure that, you know, depending on where your main focus of your work is, you will have different ideas about it. But I'll try to touch upon many future facilities that we can all be very excited about that's coming up, and that's hopefully going to give us lots of interesting neutrinos. So let's just focus a little bit more on where we are, sort of what is the scientific motivation of the topic I'm going to talk about. And we, of course, have heard several interesting contributions during this conference, so I'm certainly not going to recap all of these, but this is just to sort of focus back on, I'm really talking about sort of the high energy neutrinos. And so far, sort of this example here is sort of showing the IceCube flux as measured, the astrophysical neutrinos. And then in this constellation, you see sort of this almost famous multi-messenger plot, where it's quite interesting that the energy density sort of observed in gamma ray, in the diffuse gamma ray background, in the high energy neutrinos, and in the cosmic rays as measured by Auger is sort of on the same level, indicating a multi-messenger connection between them. And that's, of course, sort of where all those predictions for neutrino lines also hint at. We've grouped them sort of in sort of the red ones that are probably from sources such as clusters, blazars, AGNs, and all of these things that could explain a little bit of the IceCube flux, but maybe we're still waiting to see those sources. And then sort of the other half, which are the neutrinos that stem from the interaction of ultra high energy cosmic rays with various photon fields, most commonly sort of the CMB, and they will give us what they're sort of the cosmogenic neutrinos, or they're sort of the GZK effect, depending on how you want to call these. So this is where we are. And you clearly, what you also see here is that it's sort of IceCube. You would really like IceCube to measure sort of another 2 decades of energy in order to see what happens with those neutrinos. And that's what I'm going to talk about. So what are our scientific objectives? What should future neutrino telescopes and neutrino experiments deliver? And what we're really all looking forward is to resolving the high energy neutrino sky. And that means from TeV to EeV energies, really sort of to look at where do all these neutrinos come from, this tantalizing ice flux detected by IceCube. What are the sources of high energy neutrinos? Then we want to, of course, understand sort of cosmic particle acceleration. And this is where my first plot on the first slide already hinted at. We really want to understand how all of this gets together. So we want to combine what our neutrino telescopes see with alert systems and analysis with other observatories, be it gamma rays, be it radio, sort of really combine all those messengers. And ultimately, of course, we want to reveal the sources and the propagation of the highest energy particles in the universe, really also answer the questions, you know, where are ultra high energy cosmic rays from? And then lastly, probing fundamental physics with high energy neutrinos. And I'm sure if I asked many participants of this conference, they all had their favorite model, their favorite theory that they would like to test. I, of course, didn't come up with all of these. You can see sort of more about this in the IceCube white paper, where I gave the archive reference at the top. But what does that actually mean for us? What does that mean for future experiment? It means we would like an improved neutrino point source sensitivity. So we really want to be able to narrow in on the sources. we really would like to reconstruct all of these individual high energy neutrinos in almost real time. It's sort of no longer up to date to sort of, 2 years later come up with and say, hey, we found this neutrino. What I think sort of the most important one is we really need a higher collection rate than the current arrays. So especially in the energy range, sort of from 100 TeV to 10 PeV, we're really great. Sort of we have these first hints, as also reported at this conference. We really need to go into the higher collection range. And of course, sort of the successes that have been made up to the 10 PeV range, we really want to expand the energy range beyond 10 PeV to the EeV energies. So this is sort of what I wanted to highlight a little bit. And it's sort of some future detection options. This is what I'm going to go at. So I have to say, I called my talk a personal selection. I have a slightly bias towards sort of the above or towards EeV energies because I myself work in radio detection of neutrinos, and the organizers explicitly asked me that I'm free to talk about this for a while. So what happens actually at sort of energies above 10, 30 PeV, really we see that current optical detectors, be it IceCube, the future KM3net, all of these things, they're going to be a little bit too small, because what you need detectors of orders of hundreds cubic kilometers, not just 1 or 2 or 3, you really need hundreds cubic kilometers. And with optical detectors, it's quite difficult because it's limited by the attenuation length of light and sort of thereby consequently the required spacing. So you can't really, with any financial means, you can't just instrument 100 cubic kilometers of water or ice with optical sensors, because that will just have your budget explode. So of course, the next generation optical detectors can build on the past successes, and they improve their energy range a little bit because of better handle of the flux. But if you really want to go this extra mile towards EeV energies, you need a different technology. And that is sort of, in my opinion, very promising, the radio detection. So for instance, if you look at polar ice, it has, instead of sort of the tenths of meter attenuation length scale of optical light, it has radio waves have an attenuation length of kilometer scale. So you can build very sparse instrumentation that can cover large areas without sort of having to have one sort of optical detectors every 10 meters. So the radio mission has this very nice thing that is sort of confirmed by air showers and dedicated accelerator experiments. So we can build detectors based on this sort of with a very solid framework. So for those of you not so familiar with the radio emission of showers and dense media, or air showers for that matter, what are we looking for? How does this work with radio emission? So when we concentrate on ice for the time being, the word that should ring in everybody's ear is this term Ascarian effect. And it was already proposed quite a long time ago by this Mr. Ascarian. That was when really detection prospects were really rather slim, but it was it was proposed that charge accumulation in the shower front. So when your shower develops and it accumulates charge from the surrounding mediums, be it by sort of sweeping up the electrons. This charge accumulation gives rise to a current, because you have sort of the ions behind and a negatively moving charge there. So this is a current. And this current changes as the shower develops. The shower gets more particles and less particles. And from electrodynamics, everyone hopefully remembers that a changing current gives rise to a changing electric field, and that gives rise to radio emission. So what does that actually look like? The emission is nicely coherent at all frequencies and corresponding to the size of the shower. So really, because you have a shower of a certain size, it tells you it has to be sort of in the radio regime. So if you look at this figure at the top, you see that on the Cherenkov angle, you have really a large coherence. So frequencies from almost 0 megahertz all the way up to like 2 gigahertz or so. Really, it is coherence, and you get this very strong pulse, very narrow as you see it. If you move off the Cherenkov cone, you get a little less high frequencies until you're sort of 4 or 5 degrees off. Then the pulse really is concentrated on the low radio frequencies. So this is, I said now, Cherenkov angle, and this is mostly because in this dense medium, your shower is actually faster than its emission. So the index, so the speed of light is reduced in a medium, so the shower actually travels faster. So you get this effect of a Cherenkov cone and the signal on traveling on non-straight lines if you have a changing index of refraction even. So you see this here in one of our simulations at the bottom. This is what it looks like. You have sort of a neutrino come in, it interacts, it makes a shower. So for example, a hadronic shower after a neutral current interaction. And then that hadronic shower makes radio emission, which is most coherent on this red cone here. And then this cone is sort of travels through the ice, and it's sort of here in this case, some of the emissions reflected from the surface, some of it goes directly, and then it's found by a radio antenna. And this is really sort of how neutrino detection in a dense medium works. And this interesting thing is that the signal contains information in frequency, amplitude, and polarization. And that is sometimes very confusing to people who are just used to PMT signals, that actually all those parameters really help us in event reconstruction. So why is it interesting for neutrinos? So there are actually several aspects. So this is one of the old cartoons that we show here, because it's a little more complicated, but every shower that contains an electromagnetic cascade, so that means you have an hadronic shower, it contains an electromagnetic cascade or an exclusively electromagnetic shower, it creates radio emission. And so you can use a similar experimental approach for sort of very different things. For example, if you have air showers, that also contains an electromagnetic emission, so that makes radio, you can catch it with antennas. You can use it for air showers that follow neutrinos. So if you have, let's say, a tau neutrino go through a mountain, that tau neutrino interacts, makes a tau, the tau leaves the mountain, the tau makes another air shower. You take your radio antennas, you detect it. Or you go in the ice, a neutrino interacting, making a shower, and radio emission traveling through the ice. So all of these use the kilometer scale attenuation length in ice, or even better in air, where you basically have negligible radio attenuation. So this is why it's interesting for neutrinos, because you need these huge volumes, and you can really look at sort of your geometries and then make use of the large media that your neutrinos will interact in. So there are some experimental challenges, because you wonder, like, if this was this was proposed back in the 50s or in the early 60s, why does this not happen? Why have we not detected neutrinos using radio? So there are some experimental challenges, and I just want to illustrate this by some air shower signals of how back in the day, sort of in the 60s, where sort of radio air shower measurements were conducted by GALLI, you see sort of this is the technology that we work with. You had sort of an oscilloscope with a trace here, and then a little clock there, and then this blip that comes in, sort of your radio signal. They're very narrowband receivers, so this is all very complicated. And you really search for a needle in the haystack. You search for sort of this signal here, rather sort of the first pulse rather than the second pulse. And if you compare this to sort of modern day experiments, where it's sort of at the bottom, LOFAR, for example, where you have a super broadband pulse, and that's of course digitally recorded, it's a whole lot of animal. Because you're searching for these pulses, and it's typically, you need an energy of PeV or so, you're looking for a rare signal. In order to do this properly, you need high sampling speeds, you need full waveform digitization, and you want low power and a high duty cycle and all of these things. And that, of course, is not really available, has not been available so far, but with the arrival of digital electronics, things have gotten a little easier. Not everything is super easy, because sort of this is one thing I also wanted to highlight. We have a really sort of a hard time with backgrounds, so at least this is not as straightforward. So unfortunately, a lot of things make radio pulses. So I typically, sort of, when I give a lecture, you can go and, I don't know, you take a lighter, you can take your cell phone, you can take anything. So all of these make small little discharges, and we're looking sort of for milliwatt signals. So if you look at this is data from the Ariana collaboration, and you see all the triggers that were recorded, sort of millions of them within a year, and all the cosmic rays that were recorded are the ones sort of in purple at the top. You see that sort of using this correlation method, they all stick out nicely from the background, but you do have to make an effort. You can't just say we trigger and we find everything. So self-triggering does remain a challenge, and it requires quite a bit of smart algorithms. And just to give you an illustration here at the bottom, this is what I like to show. You tell me now which one is the cosmic ray and which one is not. That's a rather hard one. So we could do a poll later, but this is actually what it is. So you need good reconstruction algorithms, and site quality is important, but we're getting smarter every day, so that's helping. So how do we do radio detection of neutrinos? So I thought I started with this one channel that I talked about earlier, sort of tau neutrinos emerging from the Earth. So this little cartoon at the bottom shows you, so you have a tau neutrino, either earth skimming or through a mountain, that interacts in the material, makes a tau, and then an air shower comes out. So they're probably going to be most effective when you use mountainous terrains. So their ideas of, putting antennas everywhere, putting antennas on top of a mountain, in valleys. So this is quite interesting how sort of topography became a thing all of a sudden. So the largest challenge really, apart from building huge detectors, of course, is suppress this man-made background noise very close to the horizon. There are a couple of ongoing projects. I'm going to talk about one after. So you have really, as I said before, many different ideas, top, bottom, everything, where how one can do this, but they all follow the same approach. So you heard this already at the conference, I think, from Charles Timmermans 2 days ago. GRAND. So GRAND is, I think, really the largest idea to do this. And it has in its concept to use over 200,000 radio antennas really on a huge area. Now with sort of the idea of having several hotspots of 10,000 antennas somewhere in favorable sites. It's really going to be quite a huge endeavor. And so we're all very curious from the community that sort of the current status of GRAND Proto 300, the hardware is ready, and like everybody's suffering a little bit from this COVID approach, the COVID pandemic, so that the staged approach now is a little bit delayed, and we're all looking forward this sort of GRAND 10K, which I think will be really interesting to show whether this concept works. And I think last I heard was sort of 2025 is when we're going to see that happen. Then sort of similarly, we have beacon or Tarugi concept. And then it's sort of, it's less antennas, but sort of the topography is the other way around. They put the antennas on top of the mountain and then look down to see the signal. So we're all sort of, none of these experiments are of a size yet that we can see something, but all the prototypes are, I think, in good shape. So we move over to neutrino interactions in ice. As I said before, we may really make use of this attenuation length in the orders of kilometers. And so you can have, essentially you take one couple of, one set of antennas, and they just monitor the entire 1 kilometer, which is about the size of IceCube. So with eight radio antennas, you can basically replace IceCube. But, and this is why it had not been done before, the detection threshold is relatively high. So you need something like 10 to 30 PeV in shower energy, which is actually really the high cutoff of what IceCube has at the moment. So this is not determined by area spacing or anything. You can put your antennas closer together. It doesn't make a difference. It really is the energy at which the pulse created by the air shower, so the radio pulse we're looking for, is above the thermal noise. And the thermal noise is sort of determined by your receivers and by the ice. So, you can push it a little bit, but since the pulse amplitude goes linear with energy, it really is a steep gain here. So you need these order of 100 cubic kilometers to be sensitive to the cosmogenic neutrinos. So that's obviously not a problem because ice of 100 cubic kilometers is available in Antarctica, for example, also in Greenland. You have the advantage that human-made backgrounds are typically smaller in polar regions. So, it's not like you're building it in the middle of Venice, for example. So it has been really done. There were many early experiments, Rice, Ara, Ariana going on, and I think most famously Anita, also part of the radio in ice interaction community. And I'm going to go through a couple of them, and the idea really the same: shower in the ice, radio emission makes it to your antennas. So most neutrino limits from the radio detection in ice is not competitive to IceCube limits below 10 to the 10 GeV, and that's really because experiments have been small. They focus on proof of concept, reconstruction, all these things, and of course the likely exception is Anita, and I'm sure many of you heard about this, and this is typically the questions that I get about the Anita mystery events. Those events behave like cosmic ray signals, but they show a polarization of their little pulse that looks like a neutrino from deep through the Earth. So, and that's of course very interesting, because if these were truly a neutrino, it would first of all be a disagreement with IceCube limits. But second of all, it would be really difficult to reconcile with a standard model, and that, of course, would mean some sort of exotic particle moving through the Earth. There were some other explanations offered, ice background and anything. So, the discussion is still ongoing what it could have been. The fourth balloon, Anita 4, did see 4 events with this inconsistent polarity, but they were near the horizon, so they weren't mysteriously steep. So this little controversy is going on. So that's why I was really excited to hear when puello was funded. So puello is a anita follow-up. It's sort of basically anita 10 times more sensitive across all the energies. So we're really expecting puello to take over in sort of, if the current limits hold, from IceCube at EeV energies. So what's really great is this has this large instantaneous effective volume, and it can search for transients, point sources, and all sorts of things. And the question is now, how do they do this? Why did they not do it with anita? They did a really good job in working on trigger using an interferometric phased array. Now they do real-time digital filtering. So anita did have some problem with sort of satellites overhead and other things. So there were sort of every flight something new popped up. This is just the radio business. They put 2 times more antennas up about it and work on their pointing resolution. So puello is scheduled to fly in December 2024. We'll see how that goes with the schedule, but it's going to be really interesting what comes out of that. What are other things that are going on? This is one where I'm involved, to give a disclaimer. That is the Radio Neutrino Observatory in Greenland, or Rnog. We're going to start construction in 2021, so we're still go in the summer. Nothing COVID related has yet canceled those plans. We'll see, knock on wood. We're planning to install 35 radio stations, as you see here, near Summit Station in Greenland. And the nice thing about going to Greenland is it's sort of, we of course work with our European colleagues, but it's a Europe-led experiment with sort of everybody from the world collected. And in Greenland, it's a little bit easier than in Antarctica.
Anna?
Yeah.
You have just 5 minutes, please.
Yeah, that's fine. So we're really we expect to have the largest yearly neutrino sensitivity above 10 PeV. And we put out this concept and design paper where I encourage you all to read sort of more about it, because I can just flash this here, that we'll have very interesting sensitivity to transients and diffuse flux, sort of about 10 PeV, those plots on the side. And we're going to have sensitivity to all flavors. We're currently studying how much flavor discrimination we can do, but we're optimistic there. And sort of we may also take a look at muons from air showers and hadronic interaction models and these things. So there's a very varied science case coming with Rnog. So in the bottom, at the top again, this link to the concept paper. So if you want to read more, we're of course happy to share. So that brings me to the last part of my talk, and that's sort of one future facility that we're all very excited about, the extension of IceCube into IceCube Generation 2. The IceCube generation, or IceCube collaboration, has put out a baseline design for IceCube Gen 2. There's a big white paper, I'm sure everybody has read it, and it proposes 2 things, the significant extension of the optical array, and you see that here, sort of that blue is IceCube, and then Gen 2 IceCube optical would be this orange point, and the addition of a large radio array that's would be even at least a factor of 5 improvement over Rnog. And my optical colleagues don't like that, but I keep saying it makes IceCube look really, really small if you look at this huge radio array here. It's sort of a proposed experiment. It's not anywhere near built, but we're going through a preliminary design review expected for this fall. So that's going to be interesting for all of us. This is sort of the nice advertising plot. This is sort of the 3D idea of IceCube Gen 2 with all the different components, and a very, very great event that we're hopefully going to see. I just like this sentence that sort of we put out in the white paper, of course, a little bit PR, is sort of IceCube Gen 2 will play an essential role in shaping the new era of multi-messenger astronomy, fundamentally advancing our knowledge of the high energy universe. And what you see here is a mock-up of how IceCube will measure the neutrino spectrum if the IceCube flux continues and the GZK neutrinos cosmogenic neutrinos come in at some point, where you see really this sort of gray box, and this other box is what we have now, and this is what the spectrum with uncertainties would look like. And this is, of course, going to be amazing for this multi-messenger approach. Also, of course, there's lots of more science. I can only highlight it. There'll be flavor sensitivity. The high energies really will get unprecedented attention by IceCube Gen 2. So it's going to be really excited to go there. Of course, in terms of point sources, you'll see sort of the comparison of what IceCube Gen 2 will be able to do in comparison to IceCube. You'll see this example of the first IceCube source of TXS, how easy with Gen 2 it would have been sort of to see that the predictions coming up. I can only refer you to the white paper. So that brings us to my conclusion, or to my conclusions for the future facilities. I sort of, may be personal bias or not, the energy range beyond 30 PeV can really only be tackled by radio detectors unless somebody has a fantastic new idea of how to do this with optical and sort of much less costs. There's several upcoming experiments in the radio regime, all having sort of proposed unprecedented sensitivity. One of them, COVID permitting, will certainly be built in Greenland either this summer or next summer. IceCube is proposing to continue a success with IceCube Gen 2. And the nice thing for my part, at least, is that when sort of the communities will grow together, we'll combine optical and radio to improve on several frontiers and really make one observatory. So thank you.
Okay, thank you very much, Anna. It was a short but really intense overview of a fascinating, though rather challenging, it seems, field for the future of high energy neutrinos. I see that there are a few questions for you. Let's start with Deepak Tiwari.
Hello.
Yes.
Great talk. Okay, thank you. Great talk, Anna. And I would just like to quickly know, on slide 5, what was the software that was used for simulation of this radio Cherenkov array and this shower?
This one?
Yeah, the down one.
Yeah, so that is, it's called New Radio MC. Sorry, I didn't put a link. I should do that when I use the slide up. It's on GitHub available. Okay. It's a sort of our community software to do all of this. So all the simulations are in the same place. New Radio MC. So
New Radio MC.
Be able to find that on GitHub.
Perfect. Thank you so much.
Okay, we move then to the second question by Stefano Dusini.
Thank you. Very nice, interesting talk. I'm wondering if you can use the moon as a target of neutrino and detect a radio signal using radio telescope.
Yes, that has actually been done before, and many people propose to do that. The only problem there is sort of, the moon is of course huge, and it's a great target. However, because you're so far away, and the radio mission comes on this narrow cone, but it basically sort of just because the power, this new moon is also far away, and the power drops there with 1/r, so your energy threshold is even higher. So that means all those moon experiments that sort of happened, sort of people used before the Westerbork telescope and Lunaska, there are some places for some ideas for SKA. The ultimate problem will be that the energy threshold is even higher. So it's the same problem for Anita, that Anita is sort of, you're far away, so you need more power in your radio mission to reach you. And if you're for the moon, if you're even further away, your energy threshold is higher. So I think last I checked or so, with radio telescope, you may be able to go to like 10 to the 19.5 electron volt. So that's relatively high in energy threshold.
Okay, and finally we have Daniele Fargione, please.
Hello. Hi, I would like to remind that at the high altitude, the shower is produced in a high low density air, and therefore the splitting of magnetic field may play a role, putting the air shower into beam corn, spiraling in up and down or in left and right, and that could be an important signal. This splitting of air shower at high altitude is a relevant signature for tau. I hope you know about it.
Yeah, so I sort of, given that I had limited time, of course, for air showers, you have the two emission mechanisms. You have the Ascarian effect as well, but you also have what's called the geomagnetic effect, namely that electrons and positrons are split by the magnetic field. And of course, because this is sort of gives rise for air showers to 80% of the radio emission that you see. So all our simulations of air showers actually take the magnetic field into account to make sure that we even get emission for air showers. So that's, of course, certainly the case. And I apologize that that wasn't in my talk, just due to the briefness of time.
Okay, I agree, geomagnetic, but I want to remind that there will be the splitting of the beams, which may be observable in different way. even with the, well, I think there is the twin air shower, which is different from one air shower, which should be taken in account. That is the message.
Okay.
Okay. Okay, so thank you very much. And thank you, Anna, for this fascinating trip even to the moon and to space. And now, after hearing so much in this workshop about neutrino masses and mixings, it is time to have some concluding remarks. And I would call Stefano Ragazzi to provide for us these concluding remarks on neutrino masses and mixings.
Yeah.
Yes. So
okay.
Stefano.
So can you see my screen?
Yes.
Right. Can you see my screen?
Yeah. It seems fine. Yes.
I can.
Yes, please go ahead, Stefano.
Yeah. Sorry, I have the full screen of the okay. So. Okay, so let me thank the organizer of this conference for inviting me to give this talk. Rather than concluding remarks, okay, thank you, Antonio, for calling it concluding remarks, but they will not be concluding remarks. They are just my personal remarks that are open to
well, they are concluding because your talk is the last one
okay,
on neutrino masses and mixings.
Okay, so I will address mixing and squared mass differences and CP violations, zero neutrino double beta decay searches, and direct, I prefer to call them kinematic measurements of the effective electron neutrino mass. Okay, about mixings, squared mass difference and CP violations, we had a superb update by Antonio Marone at this workshop. I invite you to look back to his slides. It was really a remarkable review and fit of data. Let me just highlight a couple of aspects that are remarkable to me. As Antonio pointed out, there are tensions, let's call them tensions, between results of T2K and NOVA. And their consequence, weaken hints on delta and on normal ordering. The situation is that is summarized in this slide by Antonio Marone, that T2K alone prefers normal ordering, delta around 3/2 pi, and the second octant of theta 2,3. Let us forget for a while the octant of theta 2,3. NOVA alone prefers normal ordering, so apparently agrees with NOVA, but it disagrees on CP violation. NOVA prefers CP conservation. When data are combined but still looking separately at anti-neutrino data and neutrino data, you get a first surprise that the combined data of two experiments that both prefer normal ordering prefer inverted ordering. And delta 3/2 pi for antineutrino, first octant of theta through 2,3, and antineutrino, and neutrinos still prefer inverted ordering, same delta, so CP violation, and second octant of theta 2,3. So what is the conclusion? Adding data from NOVA to those of T2K shakes what we were ready to take as evidence, that is normal ordering, evidence of CP violation. NOVA alone has no evidence of CP violation. NOVA combined with T2K gives evidence of CP violation. The two combined prefer inverted ordering rather than normal ordering. That is okay. That to me shows how delicate those experiments are and how delicate data analysis, combining data are. Consider also that they are beam experiments, and we tend to believe that nothing is better controlled than in a beam experiment. So we may say it's a great opportunity for clarification for Dune and for future T2K upgrades. Okay, T2K is running meanwhile. Then let's look to what is going next. I see two privileged players in the future that are T2K plus beam upgrade plus hyper-K and Dune. They both have long-lasting physics program for and let me call them privileged in the way of fully supported by reference laboratories. This is a very strong point for any experiment. Let me go to neutrino-less double beta decay searches. For double beta, neutrino-less double beta decay searches, we had an interesting thorough review with an outlook to the future by Nando Ferroni. So I invite you to look at his slide and at the recording of his talk that is available. Let me just go through very few of his slides. Now, this one is often taken as a reference for where we are or where we need to go, where it is clear on the x-axis is the lightest neutrino mass in electron volt, and on the y-axis the effective Majorana neutrino mass as defined for double beta decay. We have different bands for inverted normal ordering. We have a degenerate region. We still live in the degenerate region, but we look in perspective to the inverted and normal ordering through the glasses of this plot. Then Nando, near to the end of his talk, came to address the lifetime sensitivity to chase for the at least next to next generation experiment. And he points out to a T1/2 10 to the 29 years with reference to the previous plot and normal ordering. That means approximately, and Nando gives a strong argument of something of the order of 100 tons of isotope, approximately, regardless of the isotope. And maybe something less, depends on the detector background. And okay, I agree that one has to forget about isotopic enrichment, since this is a technology that is not very popular, or at least the use of this technology are not very popular. Then we do not expect that it will be cheaper in the future, not at the level to produce 100 tons of enriched isotope. And then, sorry, we have this menu for the element to choose for to use for an experiment with a natural element, and the best choice looks definitely to be tellurium, natural tellurium. Let me point out for non-experts that the second in the short list, that is molybdenum. Okay, molybdenum is going to be used in at least one next generation experiment, maybe in its upgrade, but with the goal of 29 years, is better to forget about it, since it has a very strong 2 neutrino decay rate. So I completely buy the choice of Nando for natural tellurium. Then Nando's conclusion is that the only choice for such a large amount of tellurium is a, let me call Tellurium Soup, that by the way is poisonous, that is use high mass, low resolution experiment to dope it with a huge quantity of tellurium. Nando correctly pointed out that the background, the 2 neutrino double beta decay background and background from solar neutrinos will be an issue. Most of my colleagues agree that they will be an issue, and a large fraction of them prefer for this reason, what Nando called the peak squeezing approach in background reduction. However, we should not forget that Borexino recently was able to detect neutrinos from the CNO cycle as an excess of continuum over continuum background. So it's Nando's suggestion for the poisonous soup seems correct. My question is it the only choice? I'm not convinced yet that it is the only choice. Let's buy tellurium. That means scaling up by a factor order of 2 orders of magnitude quarter. That means some 100K crystals calorimeter at 10 millikelvin with at least a background reduction of a factor 100. Is it impossible or challenging? Think in a perspective of 20 years. Okay, 100K crystal calorimeter exists. It's not a millikelvin calorimeter. This is a photograph of equal calorimeter of CMS. It's a calorimeter made by 80,000 crystals. But it is run at 291 Kelvin, that is quite higher than 10 millikelvin, but a huge calorimeter, a huge crystal calorimeter with order 10 to the 2 channels exists. 100 times 10 Quore cryostat. Quore is a cryostat whose design started more than 20 years ago. It was really challenging. It was custom designed. It was not easy to put in stable operation. By the way, congratulations to Quore for the impressive duty cycle attained. Only 2 years ago, I considered not reliable the choice of the Quore cryostat for Cupid on the basis of its duty cycle at the time. Since then, they reached nearly 100% of duty cycle of core operation. But let's look in the future or in the present. Commercial millikelvin cryogenics is ramping up. They have commercial use. They have widespread use. And still, we have to experience the possible impact of quantum computing based on superconducting qubit arrays on cryogenics. So as far as the cryogenics is concerned, my approach is keep calm and carry on. Carry on what? Okay, let's address the background reduction. Background reduction, the starting point of background reduction, or let me say, of crystal bolometer calorimetry was background reduction, was a paper by Ettore Fiorini and Tapio Ninikowski. more than 35 years ago. The initial approach was had to be an extreme peak squeezing approach. Now, Quore has a resolution that is worse than a germanium resolution. That is more than 1 order of magnitude worse than you can compute from the seminal paper of Fiorini and Ninikowski. My question is, what went wrong? I received just suggestions to these questions, no quantitative explanations. Mainly or mostly, the answer were, okay, Quore, the 5 kV to be added to 5 kV acoustic noise to make 7 kV. The 5 kV Quore resolution is the best we did. Actually, the best they did along the R&D phase are a couple of crystals with 2 kV resolution. Resolution means the full width half maximum. So the question is, where is the energy escaping or trapped? My remark is that if we seek extreme performance from our detectors, we cannot be satisfied of the present understanding of our present understanding of the behavior of our present understanding of large bolometers like quark. And anyway, seeking background reduction, one has to keep in mind the long path that has been followed in background reduction by germanium-based experiment. So my message is that there is much to be done on this technique before throwing it away. Of course, if no one is going to do nothing, nothing will be improved. And things may be different. If you are open to seriously consider a fourth neutrino mass, the starting plot completely changes. Add a fourth neutrino mass, and everything changes. Normal and inverse ordering of the known neutrino masses become irrelevant. Okay. Anyway, so even if you develop the best, a very fine, very low background crystal calorimeter, 100 ton, I consider that this is the most dangerous killer. That is, look back at Masatoshi Koshiba approach to super Kamiokande. Even if proton decay doesn't exist, to Kamiokande, Kamiokande has to produce outstanding physics. The question is, or the point is, which other physics sector double beta decay experiment can address? In this regard, the Tellurium Soup may be much stronger than a higher resolution calorimeter. Okay, let me go through direct kinematic measurements of effective electron-neutrino mass. We are in a situation where a single big player exists. I would say a single player that is very big. Catherine, the challenge is summarized in this slide from Suzanne Mertens at Neutrino 2020 last summer. There is an ultra-strong, one has to deal with an ultra-strong tritium source that is, 100 gigabecquerel, and keep a background level at the level of less than 0.1 counts per second, and an energy resolution of 1 electron volt. The strategy is to look at the endpoint of the spectrum with, okay, Catherine is an integral calorimeter. Actually, it reconstructs a differential spectrum through partial integrals. Okay, this is the measurement strategy that is going, taking partial integrals with different thresholds, is what I just mentioned. Sorry.
Yes, Stefano,
yeah.
You have still 5 minutes.
Yeah. So The result now are the corresponding upper limit depends on the statistic interpretation, is less than 1 electron volt, or something like less or a bit lower than 1 electron volt, but Catherine is taking data and is improving on it. What next in the future of Catherine? They are going to search for signatures of M4 mixing with electron neutrinos through distortion on in beta decay spectrum. Electron volt scale sterile neutrinos using same data as for standard electron neutrino mass, effective electron neutrino mass, just looking to distortions in the spectrum, and KV scale neutrino mass that needs a segmented, well, KV scale means a huge counting rate on target. Probably they will have to reduce the source intensity. And to cope with the huge counting rate, they need an improved final detector, that is the segmented detector that is called Tristan. I don't know of further upgrades program, but Catherine was a real, a major success that deserve a full exploitation. A different approach that is going on, is not yet competitive with Catherine, is measure the energy, is the calorimetric measurement of the energy released in electron capture decay. And the preferred isotope now is 63 holmium. Again, you measure a spectrum. You measure the full spectrum, since you have to implant this isotope inside the microcalorimeters. Again, the game is to look to distortion on the endpoint of the spectrum due to neutrino mass. Both collaboration, ECO and Holmes, are convinced that they can, in the next few years, address an important milestone, that is the 1 electron volt sensitivity. There is no general consensus of what the cost will be of a sub-EV experiment. Sub-EV means at the scale of 0.5 or to 0.1 EV. That mainly depends on the number of channels, that in turn depends on the amount of isotope, or let us say the counting rate that you can withstand per channel. But on the huge cost that one can estimate today, we are allowed to be optimistic for important reductions due to improvement of commercial technologies. Then there are novel concepts on spectrometers that are Project 8 and Ptolemy. Project 8 is a novel approach on spectrometer. They plan to measure frequency, not energy. That is a clever approach, and it is in progress. Ptolemy is very ambitious. Initially, it was proposed as a telescope for relic neutrinos. And the effective beta electron neutrino mass would have been just a byproduct of the final goal. So it contains novel concept for tritium source, tritium embedded in a graphene foil, for a source that is more than 1,000 times more intense than Catherine source. Spectrometer, a differential high resolution spectrometer, and detector, low energy. Low energy means would have to measure electron volt electrons, not 18 keV electrons, high resolution detector. Every item has to be developed and demonstrated. I would invite the collaboration or to refrain from calling Ptolemy a neutrino telescope, at least till the 59th Neutal workshop, but Ptolemy is a remarkable proposal anyway. So my final remarks: mixing phases and squared mass difference experiments are in a privileged position, supported by the reference laboratories, making measurements and wide physics menus. Majorana double beta decay, effective double beta decay masses. Now they experience healthy competition with a variety of approaches. Some down selection between the approach, among the approaches is unavoidable. What's that you pay at least for 1 over m beta beta square? Zero background approach has to go ahead if we don't want to pay hit a systematic wall and pay for 1 over m beta beta to the 4th, as in an experiment dominated by background, by statistic fluctuation of background. And beware of single item physics menu. It can be more poisonous than the Tellurium Soup. Electron neutrino mass measurement, again, they pay for 1 over m beta square. The shores of neutrino mass spectrometers are at 50 millielectron volt, apparently not so far away, but think you pay for 1 m beta square. And it will be a huge effect for inverted ordering, a tiny effect for normal ordering. But then there is a clear target where to go is the 50 millielectron volt. Maybe people will find something earlier. Single big operating experiment, that is Catherine. It was a tremendous effort and fully exploit, and I invite to think how to fully exploit Catherine capabilities. Shores of neutrino mass spectroscopies are at 50 millielectron volts. I already mentioned that a few minutes ago.
I think, Stefano, you
okay.
To
this
converge.
is my conclusion. My concluding slides is just a summary of what I said 5 minutes ago, and many thanks for the organizer for inviting me, and many thanks to Oliviero Cremonesi, Angelo Nucciotti, Stefano Pilar, and Francesco Terranova for enlightening discussions with them. Thank you.
Thank you to you. Thank you, Stefano, for this nice and I would say thought-provoking also remarks about the future of and perspectives on neutrino masses and mixings. Let me see. It seems there are no questions. If I am correct.
One question from my side.
One question there.
Teresa.
Thank you. Yeah, I'm wondering, given what you just said about molybdenum and so on, why we should be doing Cupid et al. given that...
Well, for Cupid, the two neutrino background is not a problem. But Cupid addresses, will address the 10 to the 27 lifetime region. If you want to address a lifetime that is 100 times longer, molybdenum really becomes a problem. Molybdenum has a clear advantage now due to the high Q value that is 330 keV, that is above the dangerous 2615 keV line of 208 thallium, while while tellurium is just below it.
Yeah,
So,
but what I mean is that we will be just covering barely the inverted ordering region, and then we are not fostering a technology that maybe is expansible to larger dimensions and able to tackle the...
I'm fostering a better understanding of those detectors. Okay, what is impressive? Well, we would not have neither Core nor Cupid if the paper of 1984, the Fiorini-Nikolsky paper, would not have pointed to this kind of detectors as a much better resolution than germanium. They are still worse than germanium, because the ether approach in those days was peak squeezing. Just while in the meantime, germanium had an impressive progress also in improving the resolution, but in background reductions, reduction through other techniques. So I feel uncomfortable that my colleagues are using those detectors whose fundamental principles, or something in their fundamental principles, is still escaping to our understanding to such a large extent.
Okay, so I really hope that we don't have to wait for the 59th neutrino telescope meeting you were mentioning to know whether neutrinos are Majorana or Dirac particles. So thank you very much.
That was
really a very nice talk. And now, speaking of concluding remarks, we can move to the neutrino telescopes, concluding remarks by Teresa Montaruli, who is going to tell us everything about the future of neutrino telescopes.
Thank you, Antonio. And can you see my screen?
Not.
Sorry, Stefano, you have to stop sharing.
Yes.
Sorry, I was trying to.
Thanks.
Okay.
Okay. Yes.
Can you now see it?
Yes. Beautiful first slide.
Thank you, Antonio. So this is encouraging, because actually my task this afternoon is quite challenging, because I have to make some good thoughts about all the presentations and the nice subjects that were covered at this conference. And first of all, I would like really to thank Mauro and Elisa, because I think they did an incredible amount of work to organize this telematic conference where a lot of people, and including a lot of young people, have presented their works. So I have, just to start, to remember also that this workshop was started by Milla, and I had the pleasure to meet in person Milla and to attend this meeting many times. And I'm really missing to be in person in Venice. Clearly, I cannot summarize everything, and I had to make selections. I will just make some thoughts. And the first thing that strikes me when I consider all what was presented is that surely astroparticle physics is not at all scared of making of creating big infrastructures, and also of creating them in the most amazing locations on the Earth. And I would say that at this conference, I was impressed by this picture shown in the beautiful talk given by Kota Murase about the two observations that connected messengers. And in particular, on the left, we have the observation of the gravitational waves with the photons in different wave bands. And on the right, we have the puzzling scenario of the neutrinos from this source, TXS 0506, that was discussed a lot at this conference, together with high energy radiation, and also other bands, including the radio and the radio as well. So I have to say that for the future, so for 2023, probably if we are really lucky, we can also make a global connection. And one of the most promising sources that we can see is a core collapse supernova. And clearly this would be a fantastic thing that would teach us a lot about oscillations, about also what Irene Tamborra showed us, for instance, even the formation of black holes out of these events would be something that we could test in neutrinos and in gravitational waves. And on the right, you see the incredible work that started a lot of years ago of SNUs, and that is now described in the recent publication on the version 2 of SNUs, where essentially you can see that there can be a pre-alert coming from the neutrinos even up to one day before the big burst would start, which would also be seen in other messengers. And if we are lucky that this event is close enough, I'm talking about kiloparsecs, then this would already be visible in gravitational waves. But we have to wait for the Einstein telescope in order to connect these with gravitational waves from the full galaxy. On the other hand, there are new telescopes that will come up online in 2027, and two huge experiments, Hyper Kamiokande and Dune, are on the way to start data taking. And Gabriela Catanesi for Francesca Di Lodovico showed what are the event rates that can be expected as a function of the distance from the core collapse supernova. And you can see that there are around 100,000 events from a supernova at 10 kiloparsecs. And even if it happens in the Large Magellanic Cloud, there are still 300 events. And you can see that she showed essentially that for 5 different astrophysical models, there is a hope to identify even the ordering of the neutrinos, and similar things have been described by Giorgia Karagiorgi on Dune. Now let me come to gravitational waves, because I think they have an extremely interesting role, and they are the new telescopes at this conference. And I think that as an experimentalist, I can say that this event on the left is striking. They were surely really lucky to have one of the most beautiful events as the opening events for their fantastic start of measurements. And Barry Barish told us, look, these are raw data. We only have a passband filter to select the range of the frequencies between 35 to 350 Hertz. And on the top panel, you see the two signals arrived with some delay of a few milliseconds in the two LIGO experiments, interferometers. And you can tell from the intermediate panels that they really look like the theory. And an extremely basic formula, which gives the rate of change of the frequency, is also connected to the chirp mass, which actually allows to determine by fitting these templates of frequency change in time with this simple equation, we can get the masses of the constituent objects. Now, I make you think for a second that for the case of neutrino telescopes, we are forced to measure neutrinos indirectly, obviously, because neutrinos are neutral particles. We have to transform them in something else, which could be muons or cascades. And obviously, in doing this, we lose precision, and we know particle physics, so we can infer still all these properties of the primary particle, but we have to use Monte Carlo, we have to use probability density distributions. And so obviously, this is challenging, as Nathan Whitehorn remembered us. And continuing on the evolution of the interferometry technology that already reached an amazing sensitivity with, as you see in the plot on the left of the strain, we are at 10 to the minus 21 with the current generation, and we will push towards 10 to the minus 25 with the future generation, which is called the third generation. And already now we are doing interferometry at the level of a precision of 10 to the minus 18 meters. And this means to go beyond 3 orders of magnitude. And what Barish remembered as what is the future of gravitational waves, it's probably to have cosmology with gravitational waves. And what it means is that with the third generation, the redshift sensitivity that now is limited to about 1 will go beyond 10, and we will see a lot more of these objects that teach us a lot about general relativity, and also this will drive us towards cosmology. In what sense? Well, we had a lot of presentations of cosmology that I will not summarize because my focus is on multi-messenger. But as you see, there is an independent measurement of the Hubble constant coming from the gravitational waves. And if we think about the evolution into the Einstein telescope, probably we can even increase our precision by measuring the two polarizations. And by the way, when we will have the Einstein telescope, so one can think about a plot on the right where we are doing a cosmology by measuring the equation of state parameter as a function of the energy density of the universe in matter. Now, this plot is very well known. You can do it by yourself online, but it's showing the evolution, and this includes not only the third generation of telescopes on ground, but also space. And this means that we have a challenge to go to millions of kilometers in space and basically approach the region of the cosmology with the stochastic background. But especially we will have an enormous amount of merger events that will lead us to the precision era. And the king event is surely the event that was described in many presentations, including the enlightening presentation by Marika Branchesi, where essentially there was this event of gravitational wave emission by a merger of binary stars, so 2 neutron stars. That's happened, and after 1.7 seconds from the measurements in LIGO and Virgo as well, that allowed the triangulation and precision in the measurement of the region where the event was developing. This allowed us to also drive the optical telescopes, and actually they saw this object that was followed in time and was seen fading down. And after 1.7 seconds, Fermi measured the burst at high energy in the domain of the gamma rays, and the kilonova forming was basically the answer to the kind of event we were observing, a short gamma ray burst followed by an afterglow that was seen also in the X-rays and in the radio. And a lot of physics was extracted out of it, as Marika described. I was impressed by the story that she told us about pinning down into actually the jets that formed out of this new object that was born from these merger events. And what she said is that essentially it was possible, thanks to observations in the X-rays and also in the radio, to observe, to distinguish between two possible scenarios of an off-angle jets, but with respect to a structured jets. And actually the flux was not seen decreasing after 100 days, which would have fostered the first scenario, but rather it was increasing. And the radio observations allowed to pin down a region of the order of 2 milliarcoseconds, so that essentially it was possible to understand that most probably there is a structured jet with layers with different Lorentz factor and with lower Lorentz factor when the beam is obviously more opened. And continuing with an excellent presentation and the summary plot on the ground unified neutrino spectrum shown by Irene, here are all the neutrinos that we hope to see for the next future. And some of them we already see, like the atmospheric neutrinos. I would like to remind you that after 11 years, also Antares presented an interesting measurement of the muon and electron neutrinos at this conference. Many detectors are now the neutrino telescopes. There are people that believe that the network of these telescopes is the right solution. There are other people, and I think I am between them, that think that making them big and with VTOS is actually a very good strategy, because we can try to lower down the energy and enter more in the region where there are atmospheric neutrinos and try to see the fluxes of the sources when they are still high. And so, of course, if events are time dependent, then the network of neutrino telescopes is really relevant anyway. So I think it's a good thing that we are following both strategies. And in the next 3 years, I would say, maybe already we will have the successor of the core, which is the IceCube upgrade factor of 4 from what we see now in deep core. You see here the comparison with ORCA that is already beginning to take data. 12 strings are walking, and essentially you can see the two regions and the precision that can be achieved in red and in pink, and in the parameter space of the atmospheric neutrino oscillations, as well as we will have, now we have 250,000 atmospheric neutrinos in 8 years in deep core. So with this factor of 4 and I would say an efficiency of a factor of 10 better at 10 GeV, we can really increase the statistics to a neutrino per minute level. And then for the long baseline that we have with the atmospheric neutrinos, we can be sensitive in a few years to the ordering of the families of neutrinos. And then going back to the presentations of the neutrinos with beams, like this plot on the left is taken from the presentation of a hyper-K in 10 years. Well, you see in blue the status of T2K and the region that will be excluded in the future when we will have hyper-K. And so even for delta CP, we will be able to say something. But what I want to highlight here is the plot on the right that was shown also by Gabriella, where essentially, if we don't know the hierarchy, the neutrino oscillations in the atmosphere will also help, because with the high statistics that will be measured, essentially the region of the delta CP will be excluded at higher confidence level, even than 5 sigma. And you can see also the flavor domain here. Okay, we discussed the Glashow events in honor of Professor Glashow, but here I want to focus for a moment on the tau neutrinos, and 2 events are measured by IceCube. Are they too many, too low? This was discussed as well. I think one has to really consider that you need a big detector to do this measurement with, because to recognize these double bang events, you really have a lot of cuts and your efficiency goes down. So it is not true that we should have had more events, actually. This is a difficult analysis. And possibly, if we really have Gen 2 and KM3net and bigger detectors in the sea, we can really start thinking about oscillations from the cosmos, because these sort of measurements of neutrinos, which are undoubtedly not produced in the atmosphere, but are coming from outside, undoubtedly at the level of 3 sigma, I would say at the moment, but essentially tell us that oscillations are happening on the way to us from the sources. And by 2040, probably, we can really begin to make oscillations also with the Cosmo beams. And there were a lot of presentations, like I took one plot from one of them, comparing the standard oscillation scenario on the left. And you can see this region, the butterfly of the standard physics, let's say, where we have the different scenarios of production at the source, pion decay, muon damped, and neutron decay. And the region that we will have in 20 years is really beginning to pin down the mechanism. And then if you would have sterile neutrinos, you are sensitive also to new physics. Going back a little bit to the high energy, to the HESE events, the diffuse signal that was called a background signal of neutrinos, because this is background to astrophysical point sources of neutrinos, similarly to the background measured by Fermi in diffuse, which is a background with respect to the point sources. Well, you see now we have a considerable number of events, 102, and this is what it looks like fitting these events. You see the yellow band with a spectral index of minus 2.87. Now consider that the more the spectrum is steep, the larger is the error on fitting. And you can see the tracks, the muon tracks here, with a spectral index slightly in tension with respect to the mostly cascade events of the HESE sample. And I was really enthusiastic to see the experiment where I began to work in neutrino astronomy, Antares, measuring an intermediate value and beginning to see an excess in the diffuse measurement. Francis, with his illuminating talk, as usual, showed us these plots, which is now, let's say, some years have been spent, And this is showing a PP scenario where he said, okay, we calculated from the level of the measured flux, the points that you see in the plot on the left. If we assume that the spectrum is hard, like E minus 2.1, then we have basically concordance with what is measured by Fermi. And the energy is conserved. The two secondaries of the cosmic rays are consistent. If instead the spectrum is softer as the one we measure for the HESI, then we have an overshoot. So somehow we have to have these photons cascade down more. And a lot of the presentations that we had about are about this opaque source and this cocoon, let me say. And may I remember you that actually neutrino astronomy was born to see this sort of new window of sources that are actually not seen too much in the photons. And two scenarios were illustrated by Kota Murase, cosmic ray accelerators, so active galaxies with jets, gamma ray bursts, and then these, let's say, reservoirs of cosmic rays, of which starburst galaxies are my favorite, I would say. My favorite also because, well, because Pierre Auger told us that essentially they see an anisotropy at intermediate scale after taking into account that the horizon of the ultra-high energy cosmic rays is obviously limited by the interactions on the way. Well, they have anyway a significance of the order of more than 4 sigma for the starbursts. And then we began to think, well, maybe we should develop a catalog that includes these sources, and as well as the, let's say, most luminous and most visible also sources for IceCube, because you have to consider that IceCube has a much better sensitivity to point sources in the region of the horizon. And when we unblinded, actually Tessa Carver, my student, came to neutrino telescopes to present for the first time these results in 2019. And what we found was essentially that there was an excess in the map of the neutrinos that was coincident in the all sky search with the catalog search of 110 sources. And what you see on the right is this plot of our sensitivity and discovery potential superimposed with the upper limits. And you see some sources are beginning to have excesses. One of them is TXS that was already observed before. Already in 2018, we published the Science papers. And when you do a cumulative search of this population in the catalog of 110 sources, we obtain a significance beyond 3 sigma, which is mostly due to these sources that you see, of which one of them is M77 or NGC 1068. So this observation fostered interesting models. One of them is the corona model that was discussed in many presentations, where essentially the production, because one's own models don't work very well to explain a larger neutrino flux compared to the cascaded flux of observed in Fermi. Here, basically what is done is that the production happens in a very compact and dense region in the core close to the black hole, where the opacity is very high. Now, Kota Murase published also with colleagues these concordance plots between all the messengers. So we have the gamma rays in Fermi, we have the neutrinos in IceCube, and we have also the primaries that are producing both. And the level is the same. The energy is basically distributed coherently in the various energy regions. We have TV, PV astronomy, and we want to start EV astronomy. And today we had a beautiful talk about this, because what is important at some point is to observe this transition that you see indicated by the square, unfortunately, my mouse doesn't work all the times. And you can see that we should be able to observe this transition also in the neutrinos and to finally detect these cosmogenic neutrinos that we are waiting for, and that probably we are waiting for because of what Auger is telling us. So meaning, well, the fluxes depend on the transition and also on the fact that the composition is not proton dominated at in the anchor region, let's say. And these limits are also impressive to me from the Pierre Auger collaboration, both in the photons and also in the neutrinos, which also are received the contribution of IceCube observations as well. Let's go into the time domain now. Of course, you heard many times the story of TXS, and Francis made us aware that actually it's not the only event, but also there was an event that similarly was observed with a flare, an important flare coming in the radio of two high energy events. One was launched in the network of alerts, and essentially Fermi detected a blazar in a high state, and then also magic from ground after 5 days. And
sorry, Teresa, you have still 5 minutes.
Yes, thank you very much. And then okay, here is the multi-wavelength plot shown in the science paper, where, as I said, there is this puzzling again observation of fluxes of neutrinos and higher with respect to the level of the fluxes of the photons that would be generated also by the primary cosmic rays. And actually, the most of the problems of the one zone models for the production in the AGNs of these neutrinos came from the measurements of this 2014 and 15 flare with a high level of flux. 13 events were measured. And what we learned in this conference is also that in coincidence, let's say, with these two observations, there has been a recent publication from an optical, a network of telescopes in the optical, where essentially, first of all, for the event that was sent as an alert in the network, which was the high energy events compatible with, let's say, a PV scale neutrino, 290 is the central value, but the upper limit of its energy is up to a few PV. Well, there was a 50 in signal to noise flare in this telescope master, and then also another episode was observed in this 2014-2015 period. Now, as I said, the one zone models don't seem to explain. Of course, you need hadronic models to explain both the neutrinos and the multi-wavelength observations in the photons. But the point is that if the neutrinos are as high as the flare observed in 2014-15, then you cannot account for the multi-wavelength observations. And then what you have to do is to think about different models. For instance, again, we go into models that consider a structure in the jets. And in this case, there are various zones with a spine and a softer zone at the slower zone in the external part of the jets. And some observations in the radio that were pointed out by Anna Frankowiak actually indicate that there might be a structured jets, as well as some fantasy is needed also to see two jets in other models like the one by Britzen et al., where basically this is a collider, so two jets colliding, maybe one coming from another black hole in the vicinity. And always in the time domain, then we had another report of the analysis of the same catalog from which NGC 1068 emerged. And we have coherently that two flares are observed by TXS. NGC 1068 is not seen as a flaring source. And instead, most of the significance coming out of this search, which is in the population study at the level of 3 sigma, it comes from a few events, 3 events in the TV range, so not very high energy, coming from M87. And I don't think that I need any word to describe how beautiful is this really massive black hole with probably, again, a structured jet close to us. I didn't say much about gamma ray astronomy. Clearly,
think, you should try to
yes,
conclude.
so clearly I just want to stay tuned for the future observations from the galaxy, eventually pevatrons. And I want to remember that a lot of the experiments release the data, and this is really important. And waiting for really open observatories, we have to wait for the era of gamma ray astronomy with CTA. And so I conclude by saying that it was a pleasure to really listen to the talks of many young scientists. I hope you find along your way brilliant scientists that can teach you a lot of things. And I was so lucky to have 2 brilliant scientists during my career that taught me really a lot, and also to meet Milla, who was a bright star in multi-messenger astrophysics. And I would like to thank particularly Mauro and Elisa for all the work they have been doing.
And we thank you, Teresa, for this nice and also really vast, comprehensive review of the situation, present situation, and also the perspectives. You convinced us that the 59th neutrino telescope is really waiting for us to arrive there. Okay, so let's see if there are questions. I don't see any particular question. We are a bit late, so I would like to ask you many things, but not this time, Teresa. So thank you very much, and thank you to all the 3 speakers, because really you fascinated us this afternoon with your look at the future. Okay, now it is time to come to the awards for the flash talks, and I think that Elisa is going to tell us about the results.
Okay, thank you, Antonio. Thank you very much, and thanks all the speakers for these beautiful summaries and rich summaries. And now the most cheerful moment of this conference has come, and namely the Flash Talk Award ceremony. Thanks very much. And it's a tradition of this conference to prize, to acknowledge the best posters which have been presented in earlier editions. Now, this year we had to arrange things differently, and we believe that posters might be difficult to arrange in a digital format, and so we decided to try it out and ask for contributions as flash talks. And what happened is that we received a very, very large number of submissions. And in the end, we scheduled more than 100 flash talks. And so deciding which of those would be the best ones is certainly not an easy task. And the jury, which is composed of the local organizing and scientific committee, this week after dinner worked and watched and graded and commented on these many, many contributions. But what made the job hard is actually the fact that we did receive a very large number of very, very good talks, very well prepared, very effective, and so deciding upon them is absolutely not an easy task. And so now I'm very happy to tell you that okay, we had decided that we would acknowledge the 3 best tell you that those that we decided upon actually have received the highest marks in all the votes by the jury members. And so the winners are actually, so in alphabetical order are Andrew Morgan for his work constraining the neutral current pi-zero background for microboom single photon search. And another winner is Ilaria Risso for her preliminary study on the relative in-flight flux self-calibration for the Euclid NISP instrument. And then finally, Anna Suliga for her closer look at the PP chain reaction in the sun, constraining the coupling of light mediators to protons. Now, I would like to invite them here to join us. Unfortunately, Andrew is not present at the moment. He delivered his talk not even 6 hours ago, when it's the middle of the night for him. So I think he's well deserved getting some relief and training. So we'll have a surprise when he wakes up. But both Ilaria and Anna are connected, and so I would first like to invite Ilaria to switch her camera on and show herself.
Hi everyone, can you all see me and hear me?
Yes, I can see you very well, and I can hear you also very well. So Ilaria, we would be very grateful if you could tell us just in a few words, in a few minutes, something about your work, and so that everybody can have an idea about what you have been awarded for.
Yes, sure, thank you. And I am a PhD student in the context of the Euclid mission. And actually, I also worked on this mission even for my master thesis. And Euclid is a space mission of the European Space Agency on satellite, and it will be launched in 2022. Euclid is a mission about cosmology, and in particular, it will study the so-called dark side of the universe, meaning with this dark matter and the nature and the evolution of dark energy. And in order to do so, Euclid will observe the huge area of the sky up to redshift, mainly to redshift 2. And in particular, I focused on a specific kind of calibration of the spectrophotometer that will be mounted on the Euclid telescope. And this kind of calibration is an in-flight calibration. That is, it must be performed once the satellite is in flight. So at the moment, basically, I'm doing simulations because, of course, real data are not available yet. And basically, what I'm doing is trying through simulations to understand the best survey strategy for this kind of calibration, and in particular, how many exposures have to be taken and in which area of the sky. And recently, my group and I started introducing some complications in order to make more realistic simulations and get closer to what will be the real Euclid survey. And in particular, we started accounting for the segmentation of the detector of the spectrophotometer in different detectors, each one with its level of noise and quantum efficiency. So basically, this is what I've done and what I'm still doing now.
Okay, Lara, thank you very much. I have a question for you. I would be really curious to learn what is really the argument of what's the aspect which motivated you most to choose this topic, and what is also the aspect that you are most proud of?
Actually, I've always loved this field, and in particular, I've always thought about doing research because, in my opinion, there's nothing better than doing what you love. And actually, I've always loved science, and in particular, astrophysics. And recently, I learned that most of all, I love cosmology. So when I found out about Euclid and the opportunity to have a thesis on this space mission, I was very excited, and I understood that this was my way. So actually, I'm very, very happy to have chosen this field.
Okay, excellent. Thank you very much. Thank you very, very much. And I would like then now to invite Anna to switch her camera on. and share with us a few words about their work.
Hi, can you see me? Okay, so hello everyone. I'm Anna Swig. I'm a PhD student at the University of Copenhagen. And in my work, I focus on seeing if we can actually maybe put some limits or see if there's any sensitivity for non-standard interactions where we have the mediators that will couple to protons by looking at the neutrinos from the sun. So our sun is a great place to look for signs of new physics or a means to constrain it. And the reasons behind this are because it's the closest star to us. It has been well studied and very well measured for many, many years. But additionally, we know that better measurements will for sure come in the future. So the primary process that suffices to continuously produce the required amount of energy for our sun to shine for over 4.5 billion years, as it has been shining right now, is the fusion of hydrogen into helium. And the primary process is the PP reaction, where the key first step is fusing two protons into deuterium, electron, neutrino, and positron. However, this reaction happens very slowly, and this is because of two reasons. First, it's a weak interaction, but the second is that proton energies in our sun are actually low enough that in order for this reaction to happen, they need to penetrate repulsive Coulomb barrier. So we just know about this reaction from theoretical calculation, but it has never been measured in the laboratories. So together with my great collaborators, Shashank Chagar and George Fuller, we studied what will happen if we add a new vector boson or scalar mediator to our sun and see how they change the PP reaction. And we saw that maybe by looking at the temperature, which can be temperature of the core of our sun, which can be indirectly measured by looking at the neutrinos from the boron 8 flux, or by the CNO neutrinos that has been recently measured by the Bergsino collaboration, maybe we could even put some bounds, but more like we can see that there is some sensitivity. So the study actually aimed to see if those new standard mediators can somehow screw up the sun so much that it will no longer be compatible with the standard solar model. So yes, I would like to thank the organizers, but also my collaborators and my PhD advisor, Irene Tambora, and that is all.
Okay, Anna, thank you very much. I would like to ask you the same question. What's the reason that convinced you to choose this research field, and also what is the aspect that you're most proud of?
I think the reasons why I chose those fields is because I really like neutrinos. They are kind of like introverts among elementary particles, and I can a bit relate to that, but also they seemingly don't really have a lot of voice since they are so weakly interacting, but actually we learned that we can shed a light, for example, for the supernova physics by those tiny particles. So this is what kind of drew me to the field and what motivates me to work more on the universe.
Excellent, thank you very, very much. Now, my colleagues tell me that Andrew is actually connected. So he had abrupt wake up. And Andrew, if you are listening me and you can switch on your camera, I would be very happy to let you know that you are one of the 3 winners of the Flash Talk Award. Andrew, can you hear me?
Yeah, sorry about that. I just woke back up.
So happy rejoining. I'm very happy to let you know that you are one of the 3 winners. And if you are, if you can switch your camera on, we would be very happy to see you. And I would like to ask you if you can tell us a few words about your work and the prize, what it's about.
Oh yeah, it's well, obviously you can check out the slides I gave at 4:30 a.m. my time, but Yeah, we're looking at the neutral current delta radiative decay in the microburn experiment. And basically when you do that selection, you end up with a really big neutral current pi naught background. And so I developed a sort of sideband selection targeting neutral current pi naughts, which are of course interesting in their own respect for neutrino oscillation experiments. They're a large background for like nu mu oscillation experiments. But in this context, the idea was to constrain the systematic uncertainties on the single photon or the delta radiative decay selection. We also call them single photon events. And yeah, you can see in the slides that the correlated interaction uncertainties are reduced by quite a bit when you implement this sideband selection. So I'm very pleasantly surprised to have gotten an award for a talk that I gave at 5 a.m. my time.
And what is the reason that convinced you to choose microburn as your research?
Why did I choose microburn? Well, I was interested in neutrinos in the first place. When I got to grad school, I didn't really know what I wanted to research. So once I passed the qualifying exam, I was just sort of shopping around, and lo and behold, I got kind of lucky because a then brand new professor showed up at my university and was like, "Hey, you want to do neutrinos?" I was like, "All right." And then a couple of years later, I was at Fermilab working on microburn, and I'm still there, even though the lab is shut down, but you know.
Okay, I want to wish you, all three of you, success in your next steps. And you're going to receive an award, a paper award that we're going to send you next. And also as a gift, you're going to receive a voucher for some purchases in our university shop, where you have a selection of different items, books, or clothes, or let's say gadgets and accessories that you can freely choose from, and then we deliver them. Okay, I take the opportunity to thank all speakers, particularly those in the flash sessions, because the schedule was in the morning for us, but we had a very large number of contributions from North America as well as Asia, and an extra effort was really requested to you, and we warmly thank you for contributing to make this a very successful experience. Then I think I am finished, and congratulations to all of you. Thank you.
Okay, so congratulations also from my side, really to these young winners, and we conclude with we opened with Mauro's words, and we close with a few words from Mauro. Please, Mauro.
Okay. Good afternoon to everybody. We have to keep distances, so me and Teresa, we cannot stay together without masks. I just say a few words about this conference. First of all, it has been organized by INFN, section di Padova, and the Department of Physics and Astronomy of Padova and the University of Padova. Let me stress that this tight synergy between INFN and the university is a very powerful tool for the high energy physics in Italy. We have been sponsored by, and they not only sponsored us, but they supported our effort and encouraged us very much to organize this conference, and I'm grateful to their support. Now, we have a few numbers. We reached 967 registrations. Factor 8, our average number, that is quite huge. We claim to be the second biggest neutrino conference ever after Neutrino 2020. And I have to say we are grateful to Neutrino 2020 organizers, because they show us a direction and the way to organize this kind of conferences. We had 264 speakers. As Teresa said, we are very grateful to the speakers, very high quality talks, plenary contributed talks, flash talks. The conference is essentially work of speakers, and we enjoyed them very much. Again, in the past, we had roughly 60 speakers in the conference, so it's a factor 4 more than the average numbers. On YouTube, we had 2,500 visualization of the opening session, and roughly 400 for the commemoration session is for us a really interesting number. They are not for the public, but still they kept the attention of many people. On Slack, we had about 1,500 comments. Now, I never try to figure out how many comments have been done in a live conference, so I cannot express a ratio for this number. I'm convinced that in a live conference, this number is much used, much greater, but still having the possibility to read all the comments and to have them permanently written on Slack is a useful tool. And I think that it has been a very good idea to have them there. Also because being all the people in different time zones, offline discussion are necessary. Now, I have to thank, first of all, Pina Salente. Pina Salente is the secretary of the conference. I think that nobody of us considers Pina as a secretary. She's at full right a member of the local organizing committee, and from time to time they take the leadership of the local organizing committee. Nevertheless, I feel guilty with Pina because I underestimated the effort of this conference. The numbers are very huge. You can easily understand that managing 1,000 people, 2,600 speakers is too much work for a single person. I realized it too late because the organization never suffered for this because Pina managed to keep the organization under control at the price of working 18 hours a day. And I hope that she will have time to recover in the next days. Pina is not here, but we are going to open a few bottles of Prosecco afterwards with her. Now, we had a strong support by Sarah Magrin and Roberto Temporin. They are the multimedia managers of this room. They help us very much to set up the YouTube streaming, the Zoom sessions, and all the connection here in this room. They have been very helpful, and they gave us a great contribution. As I said at the beginning, the local organizing committee did a huge work. We are 20 people. We are a transverse community, both horizontally because the LOC are the expression of several different groups here in the Department of Physics, but also vertically, as you see, Christian and Antonio, we have people of at different stages of careers, but the collaboration has been extremely fruitful. And only for this reason, we managed to survive for this organization. Now, at the end, one should state what next. And of course, it's difficult to predict really when and in which format we will have neutrino telescopes 2023. It's difficult to plan 2 years in these days, but having a tradition of 33 years behind us and having developed such a training with this edition, I'm really sure that it will be end of February 2023. Thanks again to everybody, and see you in 2 years.
Okay, and thank you also for all those who took part really at this intense workshop. In particular, we thank those who are not in this continent because maybe they lost some hours of sleep, but for a good reason, we hope. And well, we'll see you again in 2 years from now, for sure. Okay, so have a good sleep, those who have still to sleep, and a nice day and a nice weekend for all of you. Okay, thank you very much.